Hey, this is Presh Talwalkar. They say only a genius can solve these puzzles. How many can you solve? Puzzle 1. We have a 5x5 grid of squares, and the square in the very center is shaded in blue. It is possible to draw squares of different sizes in the grid. How many squares in the grid contain the blue square? Let's work this out step by step. Let's enumerate the number of squares that contain the blue square by the size of each square. So one possibility is we have a square of size 1. So this will be just one of the small squares in the grid. And how many ways can we contain the blue square? This is the only square that will contain the blue square. There's only one of these. Now what happens if we increase the side length to be 2? Here is one such square that contains the blue square. Now this 2x2 square contains a total of 4 of these small squares. So we could easily shift this around to 4 different possibilities, and we can see that there will be 4 different squares of size 2. Now let's increase this to size 3. Here's one square that contains the blue square. Now, this 3x3 square will contain 9 of the small squares. We can shift this around, and there will be 9 different possibilities for the square of size 3 to contain this blue square in the center. So these are all the possibilities. So we will have 9 squares of this size. Now what happens when we increase the size to 4? So here's one possibility. We won't be able to have all 16 of these small squares contain this blue square because we are limited by this 5x5 grid. So there will only be 4 different possibilities where the size is equal to 4. These are the 4 possibilities. Now we will go to size 5, and there will only be one square that contains this blue square, which is the entire border of the grid. So the total number will be the sum of all these possibilities. So we have 1 plus 4 plus 9 plus 4 plus 1, and that is equal to 19 squares. And that's the answer. Puzzle 2. This problem has been shared on social media as a supposed Harvard University interview, and 90% of people were eliminated. I have serious doubts about these claims, but since this is a popular puzzle, let's go ahead and work through it. 7 men have 7 wives. Each man and each wife have 7 children. Question: what's the total number of people? So let's count the total number of people in this problem. We have 7 men, and there are 7 wives. So each man has a wife, so this will be 7 plus 7, which equals 14 people. Now comes the part that people are debating about. Each man and each wife have 7 children. So let's consider the statement that each man and each wife has 1 child. One possibility is that a man has a child and his wife has a child. But you could also imagine that you have a man and a wife that have a child, and so each man and each wife would have 1 child. Now, for my eye, if you take this first diagram, I would consider this to be that each man and each wife has 2 children, because there would be 2 children in the family. So I would eliminate this possibility. I would say the possibility on the right side is more illustrative, that each man and each wife has 1 child. So applying this logic to 7 children, we would say that there are 7 children per couple, there are 7 couples, and that will be a total of 49 children. So the total number of people will be 14 plus 49, which equals 63. I agree this problem could be up to interpretation, but this is the consensus view on the correct answer. Puzzle 3. In a race of 3 horses, the first horse beat the second horse by 11 meters and the third horse by 90 meters. If the second horse beat the third horse by 80 meters, what was the length in meters of the race. I thank Aryan Bose for the suggestion. A good way to get started in this problem is to make a couple of sketches. So let's imagine we have a race that will be equal to x meters in length. We know that the first horse beat the second horse by 11 meters. So here we have the blue ribbon horse, and we know the horse after that will be 11 meters behind. So this is the second horse. Then the third horse was beaten by 90 meters. So from the first horse, we measure 90 meters back, and this will be where the third horse is. Notice that between the second and third horses, there is a distance of 90 minus 11, which equals 79 meters. Now we also know what happens when the second horse completes the race. In this case, the second horse is at the finish line, and the second horse beat the third horse by 80 meters. So we measure 80 meters back, and this is where the third horse is. So how are we supposed to figure out the length of the race just from this information? Let's focus on these diagrams and see what information we can glean. Now notice, from the first situation to the second situation, the second horse has completed the race, which means the second horse has gone 11 meters in length. Now, in the same amount of time, we know how much the third horse has traveled. It has traveled this distance. How can we measure this distance? Well, notice that this distance plus 80 will be equal to 90. So we know that this distance must be equal to 10 meters. So we know that as the second horse travels 11 meters, the third horse has traveled 10 meters. So we can consider that if each horse is traveling at an average constant speed, we can find out the ratio of the speeds of the horses. As the third horse has gone 10 meters, the second horse has gone 11 meters. So the ratio of their speeds will be 10 over 11. Let's now form an algebraic equation to figure out the length of the race. So in the time it takes the second horse to complete the race, the second horse has gone a distance of x meters. Let's say this is equal to some time t, and we know that the time times the second horse's speed will be equal to the distance of the race. So x is equal to the second horse's speed times this time. Now, how much has the third horse gone in this amount of time? We know it trails by 80 meters, so the third horse has gone x minus 80 meters in distance. So we can set up a similar equation. The distance of x minus 80 is equal to the third horse's speed times the same time t. So now let's take the ratio of these two equations. X over 80 divided by x will be equal to the third horse's speed times t divided by the second horse's speed times t. Now in this equation, the t's will cancel out. So let's focus on this equation. We have the ratio of the third horse's speed to the second horse's speed, and we've already figured out that's equal to 10 over 11. We can now cross multiply to get 10x is equal to 11 times the group term x minus 80. All we need to do is solve for x. Let's distribute the 11, then add 880 to both sides, and subtract 10x from both sides to get that x is equal to 880. But x was a variable for the length of the course. So we know the length is equal to 880 meters. And that's the amazing answer. Puzzle 4. We have an equation written in matchsticks. 4 times 9 is equal to 46. The challenge is to move 2 sticks to make a true equation. Before I get to the answer, I want to make one clarification that I didn't think it needs to be said, but it comes up every single time I post a puzzle like this. In mathematics, an equation is a mathematical formula that expresses the equality of two expressions by connecting them with the equal sign. So you want to make sure the two sides are equal. It would not be appropriate to have something where the two sides are greater than or less than, or they are not equal to each other. We want to make a true equation. So how can we solve it? So we have 4 times 9 is equal to 46. So let's consider all of the numbers written out in matchsticks. So let's say we keep the number 4 the same. What would happen if we just change the second number? We can consider the times table of 4, and we could try to see if there's any way we can move 2 matches to get to any of these possibilities. So I don't think there's any way to do that. So let's consider the other way by keeping the 9 the same, and let's look at the 9's timetable. So let's consider all the possibilities, and there is in fact a way to get one of these possibilities to work. So let's go through the solution. So we have 4 times 9 is equal to 46. And let's go ahead and change this stick so that we go up here. And finally, let's change this stick so that we form a 5 in the end and at the beginning. So we now have the equation 5 times 9 is equal to 45. And that's the intended solution. Are there any other answers? Let us know in the comments. Puzzle 5. The puzzle will involve this diagram. A figure of equal small squares is inside a 73 by 94 rectangle. What is the side length of each square? I admit, when I saw this puzzle, I was baffled how to solve it. The solution is quite wonderful, and it is helpful to remember a construction from high school geometry. So let's say we have a square with a side length of c that's tilted. The key is to construct a square that completely contains this tilted square. The square that we have constructed is made up of 4 different congruent right triangles. Suppose the smaller side length is equal to A and the larger leg is equal to B. So all 4 of these triangles will be equal to each other. So the larger side of the square will have a length that's equal to A plus B. Now, if I could go on a little tangent here, this little diagram is the key to geometry's most important theorem. The area of this large square will be equal to the side length of this square squared. So that will be equal to the square of A plus B. But we can also calculate the area as the sum of the area of the small square inside plus the 4 triangles. So this will be equal to c squared plus 4 times 1/2 a times b. We can now expand the binomial on the left-hand side, and we can simplify 4 times 1/2 ab to be equal to 2ab. The 2ab terms will cancel on both sides, and we have the wonderful equation that a squared plus b squared is equal to c squared for any right triangle. And it's amazing how many cultures discovered this. It was known in ancient Babylon. It was also known in China as the Gogu theorem and in India as the Bodian theorem, well before it was known to the Greeks. So anyway, end of this tangent, let's solve the problem. We will construct some right triangles around these tilted squares. So let's start out by constructing one right triangle here, and let's label the legs as A and B. So on the other side of the square, we have a congruent right triangle to this. What we're going to do is we're going to figure out the horizontal and vertical lengths of this large rectangle in terms of these values of A and B. So let's go ahead and just construct some triangles so that we can get to the top of this rectangle. Okay, so now we can measure the length from the bottom to the top just in terms of these legs A and B. So we start out where we have one vertical length that's equal to B, and we are going to need to add 6 more lengths that are equal to B, so we have a total of 7B. How many legs of A do we have? We just have 2 that are here. So we can see that the length 94 is equal to 7B plus 2A. Let's do a similar construction to get from the left side of the rectangle to the right side. So we somehow need to create triangles that go from the left to the right. So we'll start out with one over here, and we'll just keep constructing triangles until we get to the right-hand side. we start out with the one length of b, and we go ahead and add the other lengths so that we have a total of 4b. Here we have one length of a, and we add these together so that we get a total of 5a. So we have the equation that 73 is equal to 4b plus 5a. The next step will be to solve for a and b. So we need to eliminate these variables. So in the second equation we have 5a, so let's multiply the first equation by 5. And in the first equation we have 2a, so let's multiply that second equation by 2. So we have the equations that 470 is equal to 35b plus 10a, and 146 is equal to 8b plus 10a. We can focus on these equations and subtract the second equation from the first. This will eliminate the 10a term, so we get that 324 is equal to 27b. Dividing both sides by 27 gives that b is equal to 12. We can substitute this into one of the equations. Let's go ahead and do it into the first equation. So 470 is equal to 35 times 12 plus 10a. All we do is we simplify this equation and we can solve that a is equal to 5. But we're not done yet. We needed to solve for the side length of the square. So of course the side length of the square will be equal to the hypotenuse of a right triangle with legs of a and b. We have that c squared is equal to a squared plus b squared. So c squared is equal to 5 squared plus 12 squared. We have a 5, 12, 13 right triangle, and therefore c is equal to 13, and the side length of each square is equal to 13 units. And that's the wonderful answer. Puzzle 6. This puzzle appeared in a Nexus 7 advertisement many years ago in Google Japan. We have the numbers 1158, and we have the following problem. Let's go ahead and use Google Lens to translate it into English. So we have a math challenge. We have 1158, and we need to use the operations plus, minus, times, and divide to get to the answer of 10. Let me just make this puzzle a little more specific. We have the four numbers 1158. You need to use each number exactly once to make the number 10, and you're allowed to use the operations of plus, minus, times, divide, and I think you should be allowed to use parentheses. You cannot use exponents. That would make the puzzle way too easy, because you could have 8 plus 1 raised to the power of 5, and that's equal to 10. So how can you do it? How can you make 10 from 1158? Let's analyze that 10 is equal to its prime factorization of 2 times 5. Now, of course, we have 5 as one of the numbers, and 1 plus 1 is equal to 2. So we could take 1 plus 1 as a group, multiply this by 5, and get to 10. But we haven't used the number 8. We need to use each number exactly once, and there's no way just to get rid of this number. So let's consider another approach. We know that 8 is equal to 2 times 2 times 2. So if we take 8 times 5, we will have 2 times 5, but then we also have 2 times 2. So let's see if we could somehow get rid of this factor of 4. Now we know that 1 plus 1 is equal to 2. So let's just start out by getting rid of one factor of 2. So we have 8 times 5 divided by the group 1 plus 1. This will be equal to 40 over 2, which will be equal to 20. So we're close, but we somehow need to modify this. So let's take this fraction and think about modifying it. What would happen if we move this 5 as a denominator on one of these ones? So let's try 8 divided by 1 plus 1 over 5. So we will get 8 divided by 6 over 5, and this will lead to 40 over 6, so that's not going to get us to 10. But what happens if instead of adding the two numbers in the denominator, we subtract the second number? So we have 8 divided by 1 minus 1 over 5. This is equal to 8 divided by 4 over 5. So here we have the factor of 4 we're looking for, which is 2 times 2. This simplifies to be 40. So we have 8 times 5 divided by 4, and that exactly gets us to the answer of 10. And that's how we do it. So just written in an inline expression, we would want 8 divided by the group, 1 minus 1 divided by 5. And this will get us to 10. And that's the answer. Puzzle 7. Here's a popular puzzle that's been spread on social media. It has the claim that only a genius can solve it. But there's also another claim that preschoolers can solve this in minutes. It takes computer programmers 10 minutes to solve it, and people with higher education will take 1 hour to solve it. So we have a pattern. 8809 is equal to 6, 7111 is equal to 0, 6666 is equal to 4, 7652 is equal to 1, 3368 is equal to 3, 9313 is equal to 1, 1008 is equal to 4, 9887 is equal to 5, 1155 is equal to 0, and what is 2021 equal to? Now, I hear from mathematicians that these puzzles sometimes annoy them because this is an improper use of the equal sign. In my experience, millions and millions of people have no problem with this, but of course we are not looking for a regular equivalence relation. We are looking for a mapping from the numbers on the left to the numbers on the right, and we're not looking for some explicit, great, finding out some grand theory of all this. This is just a simple puzzle people have fun with. We understand we're somehow transforming the numbers on the left to the numbers on the right, and this is a puzzle about number, and probably the mathematicians who don't like this will say that math isn't about numbers anyway, so don't worry if you don't like this. Math isn't about numbers for you people, but for the rest of us, this is a fun number puzzle. So what's the answer? What is 2021 equal to? So the fun thing about this puzzle, it doesn't have anything to do with the exact mathematics of the numbers. It is just a visual pattern. A child looking at the number 8809 may not think about the numerical relations, but may just look at something very superficial, like the number of holes or the number of closed loops in the digits of the number. So if we take a look at the number of holes in 8809, we will see there are exactly 6 holes in this number. So 8809 will therefore map to the number 6. So this is our proposed pattern, and let's make sure it holds for all of the other numbers. So we go back to the puzzle, and the next example we have is 7111. The digits 7 and 1 have no holes, so this number will map to the number 0. Now we have 6666. Each of the digits 6 has exactly 1 hole, so there will be 4 holes in total. In 7652, we have exactly 1 hole in the digit 6. And this pattern can be verified for all of the other numbers. 3368 will have 3 holes. So this pattern is going to be true for all of the other numbers, so all we need to do is apply it to 2021. There is exactly 1 hole in the 0, so 2021 will map to the number 1. And that's the answer. Now, of course, being a puzzle, you may have found another pattern, and I would be definitely curious if there are any other simple patterns that would give a different answer. Please let us know in the comments. Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.